Welcome to Mrs. Mahoney's podcast. This is our second one in Chapter 11, and today we're going to kind of look at some of the math that goes with acids and bases, and probably a math you're very familiar with when you've heard about the pH scale. We're going to kind of look about what does that pH really mean. So the one thing is, my packet, I realized when I got home, is not exactly the same as yours. So hopefully the problems on here, I believe they match, but if there's any bit of little kind of weirdness, we can talk about it tomorrow. I just realized I didn't have the most current on my flash drive, and I will fix that when I get to school tomorrow. But anyway, I believe we're at the top of page 6, but again, I'm not exactly sure. You just need to get to where it says acid-base pH, and this is what we're going to be starting talking about right here, is the self-ionization of water. Now, when we go back and we've talked about water, and even when we said that water was a non-conductor, a non-electrolyte, but some of those really good conductivity meters actually measured a little tiny bit of electricity. So what is going on is water will actually break into the hydrogen and the hydroxide ions and create a very small concentration. So it's a very weak electrolyte. But this is why they tell you when you have lightning, what do they tell you to do? Get out of water, because the electricity can travel through water. And then again, this is why if it's a saltwater ocean, that it's even more, because that electricity could then even travel further with something that's an ionized water, or salt water. Well, let's look at, they've figured out, okay, what volume of water do I need to have just 1 mole of these hydrogen ions? And remember, this is coming from an acid. We consider this an acidic if you have the hydrogen. Compared the same thing with the hydroxide. And what they found out in water, to get 1 mole of hydrogen ions, you need 1 times 10 to the 7th liters. So that gave you a concentration of 1 times 10 to the -7th. Same thing they found out with the hydroxide, that to get 1 mole of this hydroxide, it took the 1 times 10 to the 7th, and hence this is how this concentration came to be. Okay, something you need to add. These brackets, we're going to be using these a lot. This is a shortcut which stands for concentration. So when I see something inside of this bracket, it's telling me the concentration of that. So therefore the concentration, remember, is measured in molarity. So what they found then is, okay, if I take this Kw is called an ionization constant, and we'll look at that more definitely in AP when we look at it. But what we realize when we do an ionization constant, you only look at the aqueous. We don't look at the solid, the liquids, the gases. So since these are both liquids, the ionization constant for water really just depends on the 2 concentrations of this. So if we plug in this number for my hydrogen, plug in this number for my hydroxide, it comes what's called the ionization constant for water, and it's always, hence the word constant, of 1 times 10 to the -14th, which, looking at your power of exponents, you can see when you multiply those together, you add the exponents, that's with the -14. Okay, this is on your formula chart. This means if I know a hydrogen concentration or the hydroxide, I can figure out the other one, because this is always a constant. So let's look at these 2 problems of how I would use this. So it says determine the hydrogen and hydroxide. Okay, look at what it gave me. It gave me an acid. So what you first have to kind of look at is say, okay, HCl, this is an acid. Acids make the hydrogens, and this would be the chloride. And if I look at it, since it's only 1 proton, it's a 1-to-1 ratio, that the concentration of the hydrochloric acid is going to be the same as the concentration of your hydrogen. So just by looking at that, I know that what my concentration of the acid is the same as your hydrogen. And again, remember, some books, some places, they might be calling this the hydronium ion. It means the same thing. Sometimes it's hydronium, sometimes it's the hydrogen. And what is it? It equals 1 times 10 to the negative. As it equals 1 times 10 to the -4th molar, because it is the hydrogen ion concentration is the same as the acid concentration. So I found one of them. I found my hydrogen. But now it said, okay, I also want the hydroxide. Now I can use this relationship, plug in what I know. Well, ionization and constant of water is always 1 times 10 to the -14th equals, do I know my hydrogen? Yes, I just figured that out, times 10 to the negative fourth. I've lost some zeros there. Sorry, don't lose your zeros. This one has as many significant figures as you want. It's a constant. And times your hydroxide. That's your x, that's your unknown. So just divide both sides by 1 times 10 to the negative fourth. Rule of exponents. What do I get? 1 times 10 to the negative 10th is my hydroxide concentration. So from here I know both my hydroxide and my hydrogen concentration. Okay, look at this one. What's the difference? The only difference is now I know the hydroxide concentration. Then I can just use that, then use the same idea to find your hydrogen concentration. So I want you to do number 2, using this as a guide to realize we can find the different concentrations. Okay, well that is really good. But that would just get kind of clumsy because I don't know about you, but it was working with those times 10 to the negative 10ths. Those numbers are really, really, really small. And we're going to always have those negative exponents. So that's not very convenient. So what they've decided, and it actually is built on the consumer, for it was built more for the consumer, they said, okay, let's just take the log of everything. And if you know, logarithms are a base of 10. And so this pH scale is based then on the logarithmic scale, and they do that to get rid of those clumsy exponents. So the pH scale is what you're used to. Okay, this is what I'm looking at first, right here, the pH scale. Just look at these top numbers. And what they said is, okay, if a pH of 7, what happens at a pH of 7? I know that my hydrogen concentration is equal to my hydroxide concentration. So if both of those happens, the pH of 7, we say it's neutral. We have a neutral solution. Okay, look at right here. pH then below of 7. pH below of 7, what happens then? I have more hydrogen than hydroxide. So if you have more hydrogen concentration than hydroxide, we say below 7 is acidic. So anything below 7 is considered an acidic solution. 7 is neutral. So what happens then if you get above 7? What happens is the opposite. You have more hydroxide in there than hydrogen. So if you have more hydroxide than hydrogen, you're having more coming from the base, so we say it's basic. So anything above 7 is going to be basic, a pH of above 7. Okay, well things got kind of clumsy here, and the pH, with the log of this pH, this is the one you're most common of. You can also take the log of your POHs, or excuse me, log of your OH, and you get a POH. And that is, if you notice, there's a relationship here. 0 to the 14, 7 and 7, 14 and 0. So if you look at this relationship, it just again goes back to, I said, 10 to the negative 7th times 10 to the negative 7th equals 10 to the negative 14th. I know, but that looking at this, I can either multiply those together, or looking at this, and this is a very good one to know right here, that I know if I take the log of both of those, this is that relationship. So take the log of all of this, what do I know? That 14, if I take a pH, add it to my POH, it's always going to add up to 14. This is really, really convenient. It makes our math really easy when we start looking at this. So let's look at the formulas we've already done then. We know that KW, this is what we just did. Then we said, okay, that's really good, but if I'm doing the pH of my fish tank and I put in a pH strip, I really don't want to know times 10 to the negative 6th. 3.0 times 10 to the negative 6th. I want a number that's a little bit more user-friendly, so that's where the pH scale comes from. So here's a formula right here of how to find your pH. So this is how to find pH if they give you a log, and it's just a button on a calculator. So you need your calculator. So looking at that, you can be working these with me and you can understand where the numbers are coming from. So let's look at this. pH is just negative log of your hydrogen concentration. So down here, here's my hydrogen concentration. So how would I enter in the calculator? I would say just negative log 1 times 10 to the negative 9th. Plug that in the calculator and you should get a pH of 9.0. Okay, now with significant figures, we're not going to super stress on this, but really, technically, if you see 3 significant figures here, significant figures in pHs don't start counting until after the decimal. So technically what this is going to be, I'm going to say we're going to get away with plus or minus 1 significant figure. So if we only want to do pretty much 2 decimal places for our pHs is what we're going to do. So look at this, if I have a pH of 9, what type of solution? Well, this pH is greater than 7, so therefore I would say it is a basic solution, or a base. Okay, down here, same thing. This is my hydrogen concentration, so I'm going to enter in the calculator, negative log. Now some of you are going to love this because there's really not a lot of work to show, but then also that means there's no partial credit. You're right or you're wrong. So don't forget this negative needs to go in there. And this is on your formula chart. So negative log of 1 times 10 to the negative 6 would be 6.00. Again, I'm going to just go ahead and go to 2 decimal places. pH of 6, this we would consider an acid or acidic solution. Okay, look at here. So this is where you have to go do a little bit further and say, okay, this is an acid, and it's a 1-to-1. This is just the same as the hydrogen concentration, just like we did up above. So I'm just going to say negative log of 0.010. What do I get? 2.00. And again, this is an acidic solution. Some of you might be noticing kind of a shortcut, and if you look at a relationship, since it's just the exponent, if your coefficient is 1, if my coefficient is 1, if my coefficient is 1, it only works when my coefficient is 1, your pH is just the negative of your exponent. So look at that. That works, again, that's a nice little shortcut, but it only works, again, when the coefficient is exactly 1. Okay, let's look at some other ways you can be seeing this. And again, I know that this is spaced a little bit different, but hopefully it's the same. Look at the difference. I have OH to pH. Okay, I can't do this directly. So what am I going to have to do? I'm going to have to go from an OH. I can do exactly the same formula and find a POH, and then when I know a POH, I can find a pH. Tomorrow when we start this, I'm going to actually kind of show it in a little square. Don't have a lot of room today, and I want us to just kind of look at the formula, and tomorrow let's kind of show how these formulas are all related. I want to actually see if you guys can help me determine that and kind of come up with it so it makes more sense to you instead of me just saying write this down. Let's kind of develop it together. But this is what we're doing. So look at, to go from OH to POH, same formula, negative log of your hydroxide. So here's my hydroxide, type in the calculator, negative log. Oh, look, it has a 1. I can do my shortcut. So that means my POH is a 5. Okay, my pH scale above 7, below 7, that's pH. So before I answer this type of solution, I need to make sure I'm checking my pH. So 14 minus 5, this has a pH of 9. This is a basic solution because its pH is greater than 7. Okay, sodium hydroxide. This just means I have my hydroxide. Look at again, we're being nice, so this means it has a POH of 4. If I have a POH of 4, that means my pH is 10. Again, this is a basic solution. Okay, let's look at the lithium hydroxide. Again, this means it's just your OH. Look at this. If you want, you can either just plug that straight in the calculator. If you want, you're looking at it, you can say recognize this as 1 times 10 to the negative 3. Either way, plug it in the calculator, do it like this, get the same answer, that this is a pH of 3. POH of 3. If I have a POH of 3, my pH then is going to be 11. If I have a pH of 11, again, it's a basic solution. Okay, let's go backwards then. So if we're going backwards, guess what you do? You do the inverse on the calculator. So you have your formulas, look back on the other page and look at your formulas. And we're saying let's go in the inverse. So if I give you the pH and I want a hydronium, what's my formula? 10 to the negative pH. How do I get 10 to the negative of that X? You use inverse log. Find the button on your calculator and then make sure that you put in a negative pH or you're going to get the wrong answer. So plug that into the calculator, put in 10 to the negative 4.0 And what do I get? Now again, since there's only two numbers on the decimal, this should have two numbers, so two significant figures to the negative fourth. pH of 5, and again, if it's exactly 5, then I know I can take my shortcut to the negative fifth. Okay, buttons on a calculator. I want you to try these two, get them on the button on your calculator. Okay, look at this one, pH to pOH. This is a two-stepper, because what do I have to do? I have to go from pH, I would go to pOH, and I will then go to OH. Now, we'll talk tomorrow. Is there another way you could have done this? Yeah, and we'll kind of look at that. So pH is 14, that means my pOH 14, and the way we did this, 14 minus 14 is 0. So if I have a pOH of 14, 0, that gives me a concentration of 1. Enter it in. Say 10 to the negative 0, anything to the 0 is 1. If I have a pH of 2, that means its pOH is 12. That means my concentration here is 1 times 10 to the negative 12. Okay, again, I want you to do these two. Okay, notice we're going to go on down because not everything is always nice and neat when you're doing that. But it's still just a button on the calculator, exactly the same. You just maybe can't do these in your head. You're going to actually use your calculator. So on these, what do I want? If I have the hydrogen, what do I want? I want pH. What was my formula again? pH is negative log of your hydrogen. So when you just enter this on the calculator, you say negative log and type in 1.45 times 10 to the negative ninth, making sure you're using your EXP button or EE button. What do I get? 9.84. This is a basic solution. Okay, hydrogen, same thing. Plug this into your calculator. What do I get? 5.70. That pH is a basic solution. Okay, let's go down on here and look at what happens. OH to pH. Can I do that directly? No. I have to go in two steps. OH, go to pOH, then you can go to pH. Okay, I've stepped it out here. You probably won't see it like this on a quiz. You're going to have to recognize that you cannot go in one step. You're going to have to take two steps. So OH to pOH, same thing. If I want to find my pOH, it's just negative log of your OH. So plug it in, and what do I get? 4.60, but that's your pOH. It asks for pH. So 14 minus 4.6, 9.40. This is a basic solution. Sodium hydroxide, that's just your hydroxide. What do I know? 3.35, because I plugged it in. Subtract 14 minus that. What do I get? 10.65. This is a basic solution. Okay, you can do this one. So here we go. pH to pOH. What is that? Excuse me, to hydrogen. Remember, that was just 10 equals to the negative pH. Just a formula. It's just not going to be nice and easy. Can't do it in our head. But all we're going to do is use the button on the calculator. So enter this on the calculator. And what do I get? Again, two significant figures. 7.1 times 10 to the negative fifth. Same thing here. What do I get? 4.5 times 10 to the negative sixth. So let's just look over at these then. pH to pOH, those are the ones you go, okay, I have to do one more step. Oh man, then that one step, subtract 14. What a pain. But we got to do it because I can't just go pH to OH. There's not a shortcut. So 14 minus 3.32, 0.68. And then I could take 10 to the negative 0.68. What do I get? Because remember, that's the same formula. You just, if you have OH, you get pOH. And what do I get as a concentration? 0.21 molar. So if I have a pH of 10.45, subtract 14 minus that, and you get 3.55. Then you're going to use your calculator, 10 to the negative 3.55. What do I get? 2.81 times 10 to the negative fourth. So I've left you some to practice, and this is what we're just going to keep on working. I think you'll see the math, this part of the math, at least pH, isn't that hard at all. See you tomorrow.